Welcome everyone. My name is Professor Martin Hendry. I'm from the University of Glasgow and I'm a senior member of the LIGO scientific collaboration, which kind of means I'm a black hole hunter. So I'm an astrophysicist, but my primary interest in astrophysics these days is in using gravitational waves to tell us about the universe, in particular to probe cosmology and fundamental physics, and indeed the very nature of space-time itself using sources of gravitational waves. So I work at Glasgow University. In fact, I am Vice Principal of Glasgow University, so I don't do so much lecturing these days, but I love to talk about LIGO to the general public, to other students. So I'm delighted to have the chance to join you this evening.
Thank you very much. So this is Quantum Society. It's a really big pleasure for us to have you here. So let's enjoy, guys. Go to the video. So to start with, what's a gravitational wave? What are basically the main differences? Because everyone has heard about, water waves, sound waves, light waves, or electromagnetic, if you prefer. So can you give us a big picture for pedestrians, please?
Absolutely. So gravitational waves, we often describe them as ripples in the fabric of space-time itself. They were predicted by Albert Einstein's general theory of relativity about 100 years ago, but it took us basically 100 years to develop the technology capable of detecting them. That's because they're not like water waves or even electromagnetic waves. Those are phenomena that we think of as transferring energy through space. And even that is very interesting. How can an electromagnetic wave transport energy through empty space? That's a question that physicists were asking about 150 years ago, including a very famous Scottish physicist, James Clerk Maxwell. We'll maybe talk about him in a few minutes. Sure. But gravitational waves are even more exotic than that because they are, in some sense, actually built into the fabric of the universe itself. So we are not talking about a phenomenon that's transporting energy through the universe, through space, but actually in the fabric of space itself.
How can be 100% sure? I mean, can be noise or something. It's really typical in particle physics, for example. So how can you be 100% sure?
So detecting gravitational waves is challenging for many reasons. But one of them is exactly what you mentioned, that there are other sources of noise in our detectors which can mimic or swamp the signals that we're looking for. So fortunately, over the last few years, prior to the first detection, there were major upgrades carried out to the detectors. In fact, the UK had a major part to play in that, including some of my colleagues in Glasgow. So we're very proud of that we helped to make the LIGO detectors more sensitive, to make them capable of hearing gravitational wave signals above the noise. So we often talk about them as hearing the signals because actually the frequencies that the LIGO detectors are sensitive to correspond to frequencies that the human ear can hear. This doesn't mean that they are sound waves. They are different from sound waves. As I said a moment ago, we are not talking about energy like sound waves passing through space, but actually in the fabric of space. But because they have similar frequencies to sound waves that the human ear can hear, we can represent a gravitational wave signal as a sound. And the kinds of signals we were looking for were from things like colliding black holes. And that leads to a particular pattern of wave, a pattern of sound, if you represent it as a sound, that we call a chirp. So the short answer to your question, how could we be sure that we'd really detected gravitational waves, is that we understood enough about the pattern we were looking for, that we were able to look at what the detectors observed and to recognize that pattern. And not just in general the pattern, but the details of it, so that, for example, we could work out how massive the black holes were that collided to produce the gravitational waves. But perhaps the most important thing of all was the fact that we saw that chirp pattern in the two LIGO detectors, even though they are 3,000 kilometers apart from each other. And it was absolutely crucial that we had at least 2 detectors, because if you see that pattern in one, then yes, it could be noise. It could just be, something that looks like a gravitational wave signal, but it's just a terrestrial noise phenomenon. But when you see it in the 2 detectors separated by such a large distance, then that makes it, as best as we could judge, as sure as you can be, that it was the real deal and it wasn't just some local noise effect.
Okay, I get it. Yeah, because imagine someone with, I don't know, a podcast or something, or not someone that knows the pattern could reproduce it in one, but if it's twice exactly at the same time, taking into account special relativity, of course.
Well, good point, because it wasn't precisely the same time. There was a difference in the arrival time of about 7 milliseconds, and that was significant too, because that helps us to work out which direction the gravitational waves were coming from, always assuming that they travel at the speed of light. But we'll get back to that because that's an important question too. A few years later, in August 2017, we had another really groundbreaking event, because that time we detected 2 neutron stars colliding in gravitational waves, and we also saw the accompanying electromagnetic signature across the full spectrum from gamma rays to radio waves. So even if some people had doubts about the gravitational waves being real when the black holes collided, it was even harder to support those theories and to say, no, it's not real, it's just noise, when we also saw the neutron star merger accompanied by all those electromagnetic signals.
The next question is, I did astrophysics in my first year in physics and introduction. So dark matter, it's super slippery, right? In nature.
Yeah, sure.
We don't know what it is exactly. We have some idea. So how can LIGO be, a technology, or using the technology developed by LIGO? Could we, somehow be able to detect dark matter, or it's impossible?
No, it's an excellent question. It depends a little bit on just what the nature of dark matter is. Okay. So one of the possible candidates for dark matter, I would say probably not the most likely, but it still is possible, is that it takes the form of what we call primordial black holes. So this means black holes that formed in the very early universe, long before the formation of the lightest chemical elements. Because the lightest chemical elements like hydrogen, helium, lithium, beryllium, those were formed in the first few minutes after the Big Bang. And actually, we understand the theory of that remarkably well. And it makes it kind of hard to then sort of mess with that theory, to upset it, to mess with its predictions. If you say, wait a minute, the dark matter came much later. Instead, what we think is that the dark matter is either something that was made in the very, very early universe, and then it was kind of tucked away in the form of black holes, or if it was made later, it has to be what we call non-baryonic, which means it's not made out of protons and neutrons, it's some other kind of exotic particle. So if dark matter is non-baryonic, then, well, frankly, we don't really know what it is, but we have some ideas. If it's baryonic and in the form of these primordial black holes, then LIGO could in principle detect that. It could detect it when those primordial black holes merge. So LIGO could look directly for dark matter if it takes the form of these compact objects like black holes. The other important role that LIGO and our fellow detectors Virgo and Kagra will play in the future is to measure the expansion rate of the universe. We've already been able to do that, but only really kind of nearby. So that gives us a number, maybe you learned about this in your astrophysics class, that we call the Hubble Constant. And astronomers have been trying to measure that for nearly 100 years as well. So LIGO, Virgo and Kagra will be able to improve our measurements of the Hubble Constant in the coming years, but we also would really like to try to measure parameters that describe how much the universe is speeding up or slowing down. And those we can relate directly to how much dark matter there is, and also how much dark energy there is, which is an even weirder concept. It seems to be driving an accelerated expansion of the universe. The universe is actually speeding up in its expansion. So bottom line is there's a lot we don't know about cosmology, and we certainly hope that gravitational waves will be able to play their part in unlocking some of those mysteries.
That's true. Indeed, another guy that literally like changed the world was James Clerk Maxwell. You were talking about the Scottish physicist, and he was working at King's from 1860 to the 1865, and he published the Maxwell's equations that provide electricity and magnetism. And basically, he predicted that light was an electromagnetic wave, purely because it was like numerology, right? I mean, the speed of light was measured. He had a number using the wave equation, was the same number. You know, coincidence is quite unlikely. So, Hertz this led to the discovery by Hertz of, they exist. And the point is, could this discovery change our actual technology as much as that did, or it's unlikely? Or
if you want to make electromagnetic waves, all you've got to do is persuade electrons to accelerate up and down a wire. You know, that's what Hertz did, and he had radio waves. If we want to make gravitational waves, then the only objects we've really been able to think of that could produce that kind of space-time distortion are things like black holes and neutron stars. And, you know, you can't really carry them around in your pocket the way you can carry around a radio. So that's my cautious no, is because the nature of gravity being so much weaker than electromagnetic interactions means that to generate gravitational waves requires nature as our laboratory. You can't just do it with, you know, things that we can build in the lab.
And the next question is much more easy to answer, I hope, because it's basically what are the next steps there in LIGO, if you have any. I know you have. If you were the head of the project, where would you go next?
Our next observing run is set to begin in spring 2023, and we anticipate having significantly more detections than we've already had. So we talked about the very first one. There's actually been 90 confident detections that we've now published. We published our last catalogue in November 2021, but that was based on observations made through to March 2020. Our third observing run was April 2019 to March 2020. Since 2020, we've been beginning the process of upgrading the detectors, and our colleagues in CAGRA have been working hard to try to get CAGRA up and running as well. So once we have that network, the crucial advantage that you gain is that you've got the opportunity to pinpoint the position on the sky of the gravitational wave source more precisely, because you can basically triangulate based on the arrival time of the signal at multiple detectors. When you've only got two, you can't do that very well, but when you've got three or more, you can do it much better.
The GPS, right? It's like the...
Basically, yeah, very similar to that. We've got our fourth observing run set to begin around spring next year, and we anticipate probably detections every day or every couple of days. So give it another year and we should have accumulated a few hundred more detections. So watch this space, or maybe watch this space-time. That's all coming up within the next couple of years. And then looking further ahead, there'll be even more upgrades that will take us to our fifth observing run. That's kind of what we would regard as the design sensitivity for the advanced LIGO and Virgo and CAGRA detectors, you know, what they were designed to reach. But then plans are now emerging for what comes after that, which would be taking us into the 2030s, where there are, we hope, going to be even more sensitive detectors on the ground. And indeed, there's a plan for a spaceborne gravitational wave detector called LISA. So just like you can study light across the whole electromagnetic spectrum, and you learn much more by doing that, we also hope to learn much more by studying gravitational waves across the full gravitational wave spectrum.
Okay, thank you very much. Other question that can be really, really interesting, for example, for one of our mates, our colleagues here in Quantum Societies, Chinthi, because she wants to work in one of your projects. It's like, how can a STEM student work at LIGO or, Kagra and so on?
Yeah, well, there's a few possibilities. I mean, firstly, there are literally hundreds of graduate students working in LIGO, Virgo and Kagra. So if someone is already an undergraduate student and is thinking, well, what might I do after I graduate, then they should seriously look at what's out there by way of funded PhD places, because a lot of institutions have them. We in Glasgow would typically take on maybe 3 or 4 students every year to do funded PhD research in all aspects of our work. That's not just the astrophysics, but also the detector design and detector development. So if you're kind of happier with a spanner or a wrench in your hand, then there's plenty to do on that side as well.
This question is, I think it's really, it's like a Star Trek typical feature that you can see in a sci-fi movie or something. But basically, what would happen to us if, a gravitational wave is going to, that is produced very close to us? Imagine somehow you could have like a small black hole or something like that. And what happens if it passed through us?
The gravitational wave amplitude, it just goes as 1 over the distance. So if we're detecting 10 to the minus 18 meters from a source that's 10 to the, say, 26 meters away, then let's say it was only 10 to the 11 meters away. That would be the distance of the sun. So what you're doing is you're reducing the distance by a factor of 10 to the 15. So that means the amplitude of the gravitational wave would increase by a factor of 10 to the 15. But that only gets you to 10 to the minus 3 meters, or 1 millimeter.
1 millimeter, okay.
So even if the black holes collided at the distance of the sun, the stretching and squeezing of us would only be of order 1 millimeter. In fact, it might well be even less than that, but that's me just crudely estimating it to give a kind of upper limit on how big the effect is.
The question is, why the coincidence? Why we have that the velocity of propagation is of a gravitational wave is also the speed of light? Why?
No, this is a terrific question, because the origin of that coincidence, it isn't a coincidence, but some people might, of course, reasonably think that it is. The origin of that agreement of the speed of gravity and the speed of light is fundamentally hardwired into special relativity. The reason we have special relativity is to preserve the mathematical structure of Maxwell's equations. And what Einstein was really driving at there was that Maxwell's equations have this beautiful mathematical structure, but that structure would be disturbed, it would be messed up if the speed of light was measured to be different by different observers.
What's a really impressive explanation, and it's true. I mean, Einstein started, all special relativity, you could say, could be wrong. I mean, if it's wrong, electromagnetic as well, electromagnetism is wrong as well, because it's based completely in the Maxwell's equations, 100%. So this was the last question. Martin, I have to say, thanks 100%. Happy to be here, to have you here. It was amazing. I think it was basically one of the best lectures that I've never had.
Well, that's very kind of you. Again, I thought the questions were great.
Thank you very much. This is Quantum Society, your community of science and technology. See you soon, and I hope you enjoyed this video. See you soon.
Bye-bye.